This is video 6-2, Paramagnetism and Diamagnetism, Ionic Compounds, and the Properties of Ionic Compounds. Okay, so let's look at two things here, Paramagnetism and Diamagnetism. Okay, as the name implies, we're dealing with some kind of magnetic property. Okay, now, if a compound is paramagnetic, okay, the substance has at least one unpaired electron in the compound. Okay. And what happens as a result? The substance will be strongly attracted by a magnetic field. Okay. All compounds that end up with an odd number, total number of valence electrons is odd, has to be paramagnetic. Okay. Mathematically, there's no way you can put complete octets around every single atom. Okay. Now, if a substance is diamagnetic, okay, then all the electrons are going to be paired up. Okay, and what happens now is if you put this substance into a magnetic field, the substance would be slightly repelled by the magnetic field. Okay, so one thing that you could do, let's say you set up a couple electromagnets so you can turn them on and off. So one there and one there. Okay, and you put a substance partially in there, in between the two magnets. And you hook it up to a little scale. Okay, so you know how much it weighs. Now, if you were to turn on the magnetic fields, and if this substance was paramagnetic, it would be pulled downward, and you would see that the substance would start to weigh more. Okay, opposite, if it was diamagnetic, it would be repelled out of the magnetic field, and all of a sudden the substance would weigh less. Okay, now, just because a substance has an even number of valence electrons doesn't mean that it will be diamagnetic. Okay, what you have to do is look at the orbital configurations, the Aufbau principle or the Aufbau diagram to figure out what is actually happening. Okay, so here's an example. If you take oxygen, okay, and you were to pour some liquid oxygen in between here, okay, oxygen has basically 6 valence electrons. Okay, column 6. So 6 valence electrons in each O2. Okay, so you would expect that the liquid oxygen would actually be shot out of the magnets. Okay, but what happens when you pour some liquid O2 in there, that doesn't happen. It actually gets pulled in between and it freezes in between the magnets. Okay, now you're saying, why is that going to happen? Each oxygen has 6 valence electrons. Okay, but if we look at the Aufbau diagram, okay, for oxygen, total number of electrons in oxygen is 8 electrons total. Okay, so if we look at the 1s, the 2s, and the 2p diagrams, okay, now put the 8 electrons in there. 1, 2, 3, 4, 5, 6, 7, 8. Okay, now, yes, it's an even number, okay, and these are the 6 valence electrons, the one in the energy level 2. But the reason why oxygen is paramagnetic and not all paired up, okay, these 2 electrons are not paired up. You have 2 single electrons there. Okay, so that's why oxygen is actually paramagnetic. Okay, now, let's take a look at ionic compounds. Okay. Ionic compounds are made up of ions, okay, positively and negatively charged ions. Okay. Your ions are arranged in what's known as a crystal lattice, a nice orderly 3D repeating pattern. Okay. And you have to have opposite charged ions next to each other. Okay. You cannot put positives next to positive or negatives next to negatives. Okay. And the total charge of all the positives has to equal the total charge of all the negative ions in the ionic compound. Okay, so here's a simple lattice. This is the lithium chloride, okay, made up of lithium ions and chloride ions. And in this type of compound, it ends up in a 1-to-1 ratio. For every lithium, there's another chloride, and this makes a nice cubic crystalline structure. Okay, so this lithium is surrounded by that one, that one, that one, that one, that one, and that one. Okay, all the chloride ions. Okay, and you can pick any chloride, say this one here, and it's going to be surrounded by this one, this one, this one, this one, this one, and one more out here someplace. Okay, now they're not actually this far apart, they're actually really close together, touching. Okay, so the compound looks more like this. Okay, now, a formula unit, remember this. Okay, a formula unit is the simplest collection of atoms from which an ionic compound's formula can be established. Okay, now, the problem with saying lithium chloride is a molecule. It's not a molecule because you cannot find a single Li next to a single Cl just all by itself. Okay, next to this you'd see another Cl, above it you see another Cl, below it you see another Cl, etc. Okay, but the formula unit for LiCl is the simplest ratio, which is a 1-to-1, so 1 lithium, 1 chloride. Okay, so when we say LiCl is the formula for lithium chloride, that is actually the formula unit we're talking about. Okay. Now, ionic compounds form when neutral atoms transfer electrons. Okay. Metals, ionic compounds are usually going to be made from a metal with a nonmetal. Okay. The metal will lose an electron, and the nonmetal will gain the electrons. Okay. Now, it's not always going to be a 1-to-1 ratio. This doesn't always lose 1 and that always gains 1. Sometimes the nonmetal needs to gain 2, in which case you need 2 metal atoms for every 1 nonmetal. Okay. All the electrons have to be accounted for. If the metals are losing electrons, all the nonmetals have to gain all the electrons. Okay. Now, how do we draw Lewis structures for an ionic compound? Okay. An example, NaCl. Okay. Now, if you tried to draw a Lewis structure the way we did before, you say, well, sodium has 1 and chlorine has 7. So 1, 2, 3, 4, 5, 6, 7. Okay. You can say, oh, look, they share, and the chlorine has 2, 4, 6, 8 electrons. But the sodium would only have those 2. So that can't happen. Okay. So what happens is, instead, because this is a metal with a nonmetal, you get a transfer. Sodium starts out with 1. The chloride starts out with 7. Okay. And there is actually a transfer. There's not sharing anymore. So what this turns into then is that Na actually has no more electrons around it. Okay, no valence electrons. And the Cl ends up with 1, 2, 3, 4, 5, 6, 7, 8. Okay, and because this lost an electron, you show a positive charge. Because this gained an extra one, you put in the negative charge there. Okay, so this would be the Lewis structure for your ionic compounds, Na plus and Cl minus. Okay, now the bond is caused by the ionic bond is caused by the electrical attraction, okay, also known as an electrostatic force between the positive and the negative ions. So this transferring of the electron from the sodium does not cause the bond. Okay, it's the result. Na plus with the Cl minus. Okay, that's an arrow, not a happy face. Now, because you have a positive charge and a negative charge, this is where the attractive force comes from. Okay, and the strength of the bond, how strong the attractive force is between the positive and the negative ions, can be measured by something known as the lattice energy. Okay, now this is the amount of energy released when 1 mole of a crystalline solid is formed from gaseous ions. In other words, the lattice energy would be, for sodium chloride, Na plus in the gas phase plus Cl minus in the gas phase turns into NaCl in the solid phase plus energy. This amount of energy that is given off when these ions come together, this is known as the lattice energy. Okay, now some properties of ionic compounds. Okay, almost all of them are going to be solids at room temperature. As a matter of fact, I don't know of any that are not. Okay, and the reason why they are solids is the strong bonds that occur between the ions, which now give them a high melting and high boiling points. That's why they're solids. Okay, they're not going to vaporize at room temperature. Okay, now, even though you have strong bonds, they're actually brittle. Okay, why? If you take sodium chloride and you try and hit it with a hammer, it doesn't flatten out. It actually shatters into smaller crystals. Okay, why? What's happening? When you apply a pressure, let's say you have a crystalline solid that looks something like this. Okay, have to have opposite charges next to each other. Okay, and now, let's say you apply a force right here. Okay, so all that happens is that they just move one row down. So instead of positive being next to negative, positive next to positive, negatives next to negative, then all of a sudden you end up with something that looks like this. They moved one row down. So now the positives next to the positive, the negatives next to negative, then all of a sudden you get a repulsive force here, a repulsive force here, and it causes the thing to break apart. Okay. These will not conduct electricity in the solid state. Okay. So as long as these ions are stuck together and can't move, the compound will not conduct electricity. Okay. Now, when you melt them, it will conduct electricity very well. Okay. Now, remember this. In order for an electrical current to be produced, you have to have free-moving charged particles. Okay. The solid has charged particles, but they are not free to move, so will not conduct electricity. Once you melt it, they are free to move. Okay. And if you can dissolve the compound in water, basically now you broke them apart, so they are now again free to move. Okay. The aqueous solution, aqueous means dissolved in water. Okay, remember that. So, the solution of the ionic compound dissolved in water will conduct electricity. The ions are free to move. Okay. Now, not all ionic compounds will dissolve in water. Okay. There is an attractive force between the cations and the anions, and the water is attracted to the ions. Okay. The attraction between the ions, if they're stronger than the attraction to the water, they will break apart and it won't dissolve. Okay, so here's a salt crystal. Okay, what has to happen? Water will attach onto the sodium. Water is a polar molecule. It has positive and negative parts to it. Okay, and it can also attach onto the chloride part. Okay, and then it's now able to pull them apart. And now, because these ions are separated, they're free to move. This solution will now conduct electricity. Okay, but if you have a compound where this bond right here is stronger than the bond between the water and the molecule, the water and the ions will not be able to be broken apart, and this substance would be unable. It would not dissolve in water. Now the review. Why will both sugar and salt dissolve into water, but only the salt solution will conduct electricity? Which one of these reasons is correct?